Section 8 of the ABC of Relativity by Bertrand Russell. This LibriVox recording is in the public domain. Chapter 8. Einstein's Law of Gravitation. Before tackling Einstein's new law, it is as well to convince ourselves, on logical grounds, that Newton's law of gravitation cannot be quite right. Newton said that between any two particles of matter there is a force which is proportional to the product of their masses, and inversely proportional to the square of their distance. That is to say, ignoring for the present the question of mass, if there is a certain attraction when the particles are a mile apart, there will be a quarter as much attraction when they are 2 miles apart, a ninth as much when they are 3 miles apart, and so on. The attraction diminishes much faster than the distance increases. Now, of course, Newton, when he spoke of the distance, meant the distance at a given time. He thought there could be no ambiguity about time. But we have seen that this was a mistake. What one observer judges to be the same moment on the earth and the sun, another will judge to be 2 different moments. Distance at a given moment is therefore a subjective conception, which can hardly enter into a cosmic law. Of course, we could make our law unambiguous by saying that we are going to estimate times as they are estimated by Greenwich Observatory. But we can hardly believe that the accidental circumstances of the earth deserve to be taken so seriously. And the estimate of distance also will vary for different observers. We cannot therefore allow that Newton's form of the law of gravitation can be quite correct, since it will give different results according to which of many equally legitimate conventions we adopt. This is as absurd as it would be if the question whether one man had murdered another were to depend upon whether they were described by their Christian names or their surnames. It is obvious that physical laws must be the same whether distances are measured in miles or in kilometers, and we are concerned with what is essentially only an extension of the same principle. Our measurements are conventional to an even greater extent than is admitted by the special theory of relativity. Moreover, every measurement is a physical process carried out with physical material. The result is certainly an experimental datum, but may not be susceptible of the simple interpretation which we ordinarily assign to it. We are therefore not going to assume to begin with that we know how to measure anything. We assume that there is a certain physical quantity called interval, which is a relation between two events that are not widely separated. But we do not assume in advance that we know how to measure it, beyond taking it for granted that it is given by some generalization of the theorem of Pythagoras, such as we spoke of in the preceding chapter. We do assume, however, that events have an order, and that this order is 4-dimensional. We assume, that is to say, that we know what we mean by saying that a certain event is nearer to another than to a third, so that before making accurate measurements we can speak of the neighborhood of an event. And we assume that, in order to assign the portion of an event in space-time, 4 quantities, coordinates, are necessary, e.g., in our former case of an explosion on an airship, latitude, longitude, altitude, and time. But we assume nothing about the way in which these coordinates are assigned, except that neighboring coordinates are assigned to neighboring events. The way in which these numbers, called coordinates, are to be assigned is neither wholly arbitrary nor a result of careful measurement. It lies in an intermediate region. While you are making any continuous journey, your coordinates must never alter by sudden jumps. In America, one finds that the houses between, say, 14th Street and 15th Street are likely to have numbers between 1400 and 1500. While those between 15th Street and 16th Street have numbers between 1500 and 1600, even if the 1400s were not used up. This would not do for our purposes, because there is a sudden jump when we pass from one block to the next. Or again, we might assign the time coordinate in the following way. Take the time that elapses between 2 successive births of people called Smith. An event occurring between the births of the 3000th and the 3001st Smith known to history shall have a coordinate lying between 3000 and 3001. The fractional part of its coordinate shall be the fraction of a year that has elapsed since the birth of the 3000th Smith. Obviously, there could never be as much as a year between two successive additions to the Smith family. This way of assigning the time coordinate is perfectly definite, but it is not admissible for our purposes because there will be sudden jumps between events just before the birth of a Smith and events just after, so that in a continuous journey your time coordinate will not change continuously. It is assumed that independently of measurement, we know what a continuous journey is. And when your position in space-time changes continuously, each of your 4 coordinates must change continuously. 1, 2, or 3 of them may not change at all, but whatever change does occur must be smooth, without sudden jumps. This explains what is not allowable in assigning coordinates. To explain all the changes that are legitimate in your coordinates, suppose you take a large piece of soft India rubber. While it is in an unstretched condition, measure little squares on it, each 1/10 of an inch each way. Put in little tiny pins at the corners of the squares. We can take as 2 of the coordinates of one of these pins the number of pins passed in going to the right from a given pin until we come just below the pin in question, and then the number of pins we pass on the way up to this pin. In the figure, let O be the pin we start from, and P the pin to which we are going to assign coordinates. P is in the 5th column in the 3rd row, so its coordinates in the plane of India rubber are to be 5 and 3. Now take the India rubber and stretch it and twist it as much as you like. Let the pins now be in the shape they have in figure 2. The divisions now no longer represent distances according to our usual notions, but they will still do just as well as coordinates. We may still take P as having the coordinates 5 and 3 in the plane of the India rubber, and we may still regard the India rubber as being in a plane, even if we have twisted it out of what we would ordinarily call a plane. Such continuous distortions do not matter. To take another illustration, instead of using a steel measuring rod to fix our coordinates, let us use a live eel, which is wriggling all the time. The distance from the tail to the head of the eel is to count as 1 from the point of view of coordinates, whatever shape the creature may be assuming at the moment. The eel is continuous, and its wriggles are continuous, so it may be taken as our unit of distance in assigning coordinates. Beyond the requirement of continuity, the method of assigning coordinates is purely conventional, and therefore a live eel is just as good as a steel rod. We are apt to think that for really careful measurements it is better to use a steel rod than a live eel. This is a mistake, not because the eel tells us what the steel rod was thought to tell, but because the steel rod really tells no more than the eel obviously does. The point is, not that eels are really rigid, but that steel rods really wriggle. To an observer in just one possible state of motion, the eel would appear rigid, while the steel rod would seem to wriggle just as the eel does to us. For everybody moving differently both from this observer and ourselves, both the eel and the rod would seem to wriggle. And there is no saying that one observer is right and the other wrong. In such matters, what is seen does not belong solely to the physical process observed, but also to the standpoint of the observer. Measurements of distances and times do not directly reveal properties of the things measured, but relations of the things to the measurer. What observation can tell us about the physical world is therefore more abstract than we have hitherto believed. It is important to realize that geometry, as taught in schools since Greek times, ceases to exist as a separate science and becomes merged in physics. The 2 fundamental notions in elementary geometry were the straight line and the circle. What appears to you as a straight road, whose parts all exist now, may appear to another observer to be like the flight of a rocket, some kind of curve, whose parts come into existence successively. The circle depends upon measurement of distances, since it consists of all the points at a given distance from its center. And measurement of distances, as we have seen, is a subjective affair, depending upon the way in which the observer is moving. The failure of the circle to have objective validity was demonstrated by the Michelson-Morley experiment, and is thus, in a sense, the starting point of the whole theory of relativity. Rigid bodies, which we need for measurement, are only rigid for certain observers, For others, they will be constantly changing all their dimensions. It is only our obstinately earthbound imagination that makes us suppose a geometry separate from physics to be possible. That is why we do not trouble to give physical significance to our coordinates from the start. Formerly, the coordinates used in physics were supposed to be carefully measured distances. Now we realize that this care at the start is thrown away. It is at a later stage that care is required. Our coordinates now are hardly more than a systematic way of cataloging events. But mathematics provides, in the method of tensors, such an immensely powerful technique that we can use coordinates assigned in this apparently careless way just as effectively as if we had applied the whole apparatus of minutely accurate measurement in arriving at them. The advantage of being haphazard at the start is that we avoid making surreptitious physical assumptions, which we can hardly help making if we suppose that our coordinates have initially some particular physical significance. We assume that if two events are close together, but not necessarily otherwise, there is an interval between them which can be calculated from the differences between their coordinates by some such formula as we considered in the preceding chapter. That is to say, we take the squares and products of the differences of coordinates, we multiply them by suitable amounts, which in general will vary from place to place, and we add the results together. The sum obtained is the square of the interval. We do not assume in advance that we know the amounts by which the squares and products must be multiplied. This is going to be discovered by observing physical phenomena. We know, however, certain things. We know that the old Newtonian physics is very nearly accurate when our coordinates have been chosen in a certain way. We know that the special theory of relativity is still more nearly accurate for suitable coordinates. From such facts we can infer certain things about our new coordinates, which, in a logical deduction, appear as postulates of the new theory. As such postulates we take 1. That every body travels in a geodesic in space-time, except insofar as electromagnetic forces act upon it. 2. That a light ray travels so that the interval between two parts of it is 0. 3. That at a great distance from gravitating matter we can transform our coordinates by mathematical manipulation so that the interval shall be what it is in the special theory of relativity, and that this is approximately true wherever gravitation is not very powerful. Each of these postulates requires some explanation. We saw that a geodesic on a surface is the shortest line that can be drawn on the surface from one point to another. For example, on the Earth the geodesics are great circles. When we come to space-time, the mathematics is the same, but the verbal explanations have to be rather different. In the general theory of relativity, it is only neighboring events that have a definite interval, independently of the route by which we travel from one to the other. The interval between distant events depends on the route pursued, and has to be calculated by dividing the route into a number of little bits, and adding up the intervals for the various little bits. If the interval is space-like, a body cannot travel from one event to the other. Therefore, when we are considering the way bodies move, we are confined to time-like intervals. The interval between neighboring events, when it is time-like, will appear as the time between them for an observer who travels from the one event to the other. And so the whole interval between two events will be judged by a person who travels from one to the other to be what his clock show to be the time that he has taken on the journey. For some routes this time will be longer, for others shorter. The more slowly the man travels, the longer he will think he has been on the journey. This must not be taken as a platitude. I am not saying that if you travel from London to Edinburgh, you will take longer if you travel more slowly. I am saying something much more odd. I am saying that if you leave London at 10 a.m. and arrive in Edinburgh at 6:30 p.m. Greenwich time, the more slowly you travel, the longer you will take, if the time is judged by your watch. This is a very different statement. From the point of view of a person on the earth, your journey takes 8.5 hours. But if you had been a ray of light traveling round the solar system, starting from London at 10 a.m., reflected from Jupiter to Saturn, and so on, until at last you were reflected back to Edinburgh and arrived there at 6:30 p.m., you would judge that the journey had taken you exactly no time. And if you had gone by any circuitous route, which enabled you to arrive in time by traveling fast, the longer your route, the less time you would judge that you had taken. The diminution of time would be continual as your speed approached that of light. Now I say that when a body travels, if it is left to itself, it chooses the route which makes the time between two stages of the journey as long as possible. If it had traveled from one event to another by any other route, the time, as measured by its own clocks, would have been shorter. This is a way of saying that bodies, left to themselves, do their journeys as slowly as they can. It is a sort of law of cosmic laziness. Its mathematical expression is that they travel in geodesics, in which the total interval between any two events on the journey is greater than by any alternative route. The fact that it is greater, not less, is due to the fact that the sort of interval we are considering is more analogous to time than to distance. For example, if a person could leave the earth and travel about for a time and then return, the time between his departure and return would be less by his clocks than by those on the earth. The earth, in its journey round the sun, chooses the route which makes the time of any bit of its course by its clocks longer than the time judged by clocks which move by a different route. That is what is meant by saying that bodies left to themselves move in geodesics in space-time. We assume that the body considered is not acted upon by electromagnetic forces. We are concerned at present with the law of gravitation, not with the effects of electromagnetism. These effects have been brought into the framework of the general theory of relativity by Weyl, but for the present we will ignore his work. The planets, in any case, are not subject, as wholes, to appreciable electromagnetic forces. It is only gravitation that has to be considered in accounting for their motions, with which we are concerned in this chapter. Our second postulate, that a light ray travels so that the interval between two parts of it is zero, has the advantage that it does not have to be stated only for small distances. If each little bit of interval is zero, the sum of all of them is zero, and so even distant parts of the same light ray have a zero interval. The course of a light ray is also a geodesic, according to the definition. Thus, we now have two empirical ways of discovering what are the geodesics in space-time, namely light rays and bodies moving freely. Among freely moving bodies are included all which are not subject to constraints or to electromagnetic forces, that is to say, the sun, stars, planets, and satellites, and also falling bodies on the earth, at least when they are falling in a vacuum. When you are standing on the earth, you are subject to electromagnetic forces. The electrons and protons in the neighborhood of your feet exert a repulsion on your feet which is just enough to overcome the earth's gravitation. This is what prevents you from falling through the earth, which, solid as it looks, is mostly empty space. The third postulate, which relates the general to the special theory, is very useful. It is not necessary for the application of the special theory to a limited region that there should be no gravitation in the region. It is enough if the intensity of gravitation is practically the same throughout the region. This enables us to apply the special theory within any small region. How small it will have to be depends upon the neighborhood. On the surface of the earth, it would have to be small enough for the curvature of the earth to be negligible. In the spaces between the planets, it need only be small enough for the attraction of the sun and the planets to be sensibly constant throughout the region. In the spaces between the stars, it might be enormous, say half the distance from one star to the next, without introducing measurable inaccuracies. At a great distance from gravitating matter, we can so choose our coordinates as to obtain a Euclidean space. This is really only another way of saying that the special theory of relativity applies. In the neighborhood of matter, although we can make our space Euclidean in any small region, we cannot do so throughout any region within which gravitation varies sensibly. At least, if we do, we shall have to abandon the view that bodies move in geodesics. In the neighborhood of a piece of matter, there is, as it were, a hill in space-time. This hill grows steeper and steeper as it gets nearer the top, like the neck of a champagne bottle. It ends in a sheer precipice. Now, by the law of cosmic laziness, which we mentioned earlier, a body coming into the neighborhood of the hill will not attempt to go straight over the top, but will go round. This is the essence of Einstein's view of gravitation. What a body does, it does because of the nature of space-time in its own neighborhood, not because of some mysterious force emanating from a distant body. An analogy will serve to make the point clear. Suppose that on a dark night a number of men with lanterns were walking in various directions across a huge plain, and suppose that in one part of the plain there was a hill with a flaring beacon on the top. Our hill is to be such as we have described, growing steeper as it goes up and ending in a precipice. I shall suppose that there are villages dotted about the plain, and the men with lanterns are walking to and from these various villages. Paths have been made, showing the easiest way from any one village to any other. These paths will all be more or less curved, to avoid going too far up the hill. They will be more sharply curved when they pass near the top of the hill than when they keep some way off from it. Now suppose that you are observing all this, as best you can, from a place high up in a balloon, so that you cannot see the ground, but only the lanterns and the beacon. You will not know that there is a hill, or that the beacon is at the top of it. You will see that people turn out of the straight course when they approach the beacon, and that the nearer they come, the more they turn aside. You will naturally attribute this to an effect of the beacon. You may think that it is very hot and people are afraid of getting burnt. But if you wait for daylight, you will see the hill, and you will find that the beacon merely marks the top of the hill, and does not influence the people with lanterns in any way. Now, in this analogy, the beacon corresponds to the sun, the people with lanterns correspond to the planets and comets, the paths correspond to their orbits, and the coming of daylight corresponds to the coming of Einstein. Einstein says that the sun is at the top of a hill, only the hill is in space-time, not in space. I advise the reader not to try to picture this, because it is impossible. Each body, at each moment, adopts the easiest course open to it, but owing to the hill, the easiest course is not a straight line. Each little bit of matter is at the top of its own little hill, like the cock on his own dung heap. What we call a big bit of matter is a bit which is at the top of a big hill. The hill is what we know about. The bit of matter at the top is assumed for convenience. Perhaps there is really no need to assume it, and we could do with the hill alone, for we can never get to the top of anyone else's hill any more than the pugnacious cock can fight the peculiarly irritating bird that he sees in the looking-glass. I have given only a qualitative description of Einstein's law of gravitation. To give its exact quantitative formulation is impossible without more mathematics than I am permitting myself. The most interesting point about it is that it makes the law no longer the result of action at a distance. The sun exerts no force on the planets whatever. Just as geometry has become physics, so, in a sense, physics has become geometry. The law of gravitation has become the geometrical law that every body pursues the easiest course from place to place, but this course is affected by the hills and valleys that are encountered on the road. End of section 8.